uh, Dr. Jamie Townsend. He's from Cranfield University, UK, and is also part of ISCFD. So before moving on to the presentation, um, from all the people in the organizing committee, we would like to thank Jamie for taking time and effort to really put up this interesting presentation, which I'm also very keen and looking forward to. So before we get started, I would urge uh, the representative from ISCFD today, Jesus, to give a brief introduction about what ISCFD is, and then I will also give a brief introduction about BosonQ Psi, and then we will be getting started.
Thank you, Abhishek, for the introduction. As Abhishek said, my name is Jesus, a member of the board of the ICFT Society, the International Society for Computational Fluid Dynamics, and I would just like to kindly introduce you the purpose of our society, which is mainly to spread the knowledge of CFD and link the knowledge of this field with experts of the field and enthusiasts of the field. In order to do so, we are focused on organizing events. In the past, we used to organize them back at the University of Cranfield, and now, due to the current situation, we are mainly focused on organizing webinars as our partners from BosonQ. Without further ado, I will leave you with Abhishek again, so he can introduce you to his organization. Thank you again, Abhishek.
Thank you, Jesus, for that brief and great introduction about ISCFD. I just want to highlight that ISCFD is a very integral part of this Quantum Winter event, and everybody from ISCFD has been working very hard to put up this whole event, and hopefully this will turn out to be great as we are coming close to the hackathon part of the event soon. So this will be the third last talk for everyone. This event will be counted towards your attendance if you haven't attended any or have attended or still left to attend the 2 out of the 5 that we have. So just to remind, we had our first on 7th November. Then we had on 21st November our second one. Then the third one was yesterday, and today is the fourth one. Sorry, I missed something there. So 7, 20, yes. So and then we will have our next one, which will be passed on. The information will be passed on soon, which will be on 2nd December. Hopefully, the dates are still not confirmed. And then then it is everybody's has to attend the fifth lecture, the last lecture, which is on December 5, and then we will be starting with our hackathon. So just to start with the presentation, a brief introduction about BosonQ Psi. So we are a young and dynamic startup based in India, and we started in September, and we basically work on a very niche area of multiphysics simulations and quantum computing, and that's why we arranged this event, because many people in the quantum realm do not know about multiphysics, and this will be a great introduction to them on different aspects of multiphysics simulations, where one of the interesting ones that we are going to hear today from Jamie would be astrophysics. And also it is for the multiphysics community to know the possibilities that quantum computing will bring in. So without further ado, let's get started with today's presentation. Again, I would like to thank Jamie for really putting up this really interesting talk here. I'm really looking forward to that. Jamie, it's all yours now.
Great. Thank you very much, Abhishek, and thank you, Jesus, for the introductions. Good evening, everyone. It's a pleasure to speak with you this evening from the UK. And as Abhishek said, I also agree. I think this is a very interesting area of multiphysics simulations. And so I put up this title, How to Test the Untestable. And that perhaps sounds a bit provocative, maybe even a bit arrogant. but there is some meaning behind that, and hopefully that will become quite clear later on. And so, just as a full disclaimer before we begin, I'm not an astrophysicist. Okay, like I've actually never taken an astrophysics like formal course in my life. But just like you don't need to be a pilot to design an aircraft, you don't need to be an astrophysicist to build and research the tools that astrophysicists need. And as we'll come to see, a couple of different areas of multiphysics will join up, and we can then start to build things for astrophysicists for them to use. So let's just jump right into astrophysics, because astrophysics is cool and I want to show you some pictures. So here we go. So I put a range of different things going on here, and I'll give a brief description of them one by one. So let's start top left. So we have a wind nebula. This is in particular, it's called the Crab Nebula. It's quite a famous astrophysical phenomenon, and basically this thing is huge, right? It's absolutely huge, and at the center of it is a neutron star. And a neutron star is a very small body, but it's extremely dense. Okay, so it has a very strong gravitational field. And in this particular case, the neutron star, it spins, right? It's spinning and spinning and spinning. And in the process of this, it's spewing out all of this stuff. And it comes together and it creates this awesome picture. And in this case, the gas may be traveling 70-ish% of the speed of light. So we have a really violent scenario here. And it's beautiful to look at. And I'm sure for astrophysicists, it's amazing to study. If we go to the top right, gravitational waves. This is kind of something that's become popular recently. And what we have in this picture is, say, two dense things. So maybe it's two neutron stars, for example, two black holes, and they're just spinning around each other. And because they're so dense, it creates ripples in the fabric of space-time. So we'll talk a little bit about that more later, but like it's something that astrophysicists are very keen to study now, and there have been Nobel Prizes recently because we were able to detect them. They were predicted by Einstein's theory of general relativity, and we've now been able to measure it and prove that they exist. Bottom left, we have something like the sun. So this is a simulation or a snapshot of a simulation of some solar activity. So the sun is, of course, this hot ball of plasma, and it's constantly moving around. It's never stationary. And physicists might want to understand the sun better, try to predict the life of the sun, and just try to learn what's going on really there. And then moving right again, back to black holes, we have this accretion. So in the center is, well, the black hole, and it's where it's such a strong gravitational field, it's drawing matter in, and it kind of forms this accretion disk around it. And lots of interesting and scary things happen there. But again, this is another hot topic that physicists want to study. And then moving on to the one on the right-hand side, the star formation. So pretty much, whenever I talk to an astrophysicist, I would say about 70% of them, when I ask them what they do, they tell me star formation. It's a very popular topic, particularly among, in my opinion, what it seems, particularly among young astrophysicists. And so, based on my understanding, what we're looking at here is a filament. And this is a huge scale. This thing is huge. And in this center region here, where it's a bit brighter, there might be a star about to form there. And simulations are used to predict this, okay? So it kind of brings me back to my original point, how to test the untestable. Because as you've already kind of gathered, the environments that these things exist in, they are kind of beyond our comprehension, really. Like it's really hot, it's really fast, it's there's lots going on. Human life would not survive near here, so we can't make an experiment to, I don't know, we can't make a black hole in a laboratory and do some experiments there. So what can we do, right? Well, I keep pressing the wrong button. Okay. So there are a couple of techniques that are used, right? And I'm just going. This is not an exhaustive list, but let's start with astronomy. So what we can see, we can, right, with our own eyes. You know, what can we observe out in the universe? All right, and that's something we probably did as a kid, looking at the moon or whatever. And then we have radio astronomy. So radio astronomy is just essentially another way of scanning the night sky and seeing what we can pick up through radio waves, things that we perhaps can't see or can't study in much detail through optical astronomy. So it's like, okay, I can look up at the sky and I can see an airplane, but also I can look on my phone or look on a radar, and I can get new information about the altitude and the velocity of the airplane that I can't get just from looking at it. Okay, so it kind of helps to build up more of a picture of what's going on. And then gravitational wave astronomy. This is like, well, to continue the analogy of the airplane, this is like listening. Like I can see there's a plane flying, or perhaps I can't see it, but I can listen. And most of you, I'm sure, when you're listening to a plane fly overhead, you can tell the difference between a small aircraft and a fighter jet. You know, they sound different. And this is what the LIGO facility, which is in this picture, which is detecting gravitational waves, is doing. And there are people who, they can listen to the signals picked up at LIGO, and they can tell you whether you're listening to two neutron stars or a black hole and a neutron star spinning around each other. It's quite, I don't know how they do that. I assume these people are also very talented musicians as well. But again, these three methods that I point out here help to build up a picture of the universe. The problem is that it's what we can observe. It's something that's already happened, right? So it's not like you can test a hypothesis. So you can create some theory here. This is the other way. You have some theory, and then you can use the data that you've collected from your astronomy to try and dispute that theory. But you know, there's something missing here, and I'm very sorry. I'm gonna say something. There's somebody not muted who's a bit noisy. Sounds like they've fallen asleep already. If you are not muted, please can you do it? It's a bit distracting. No worries. Okay, so moving on. Computational astrophysics, what it then does is it enables you to bridge the gap between theory and observations. So it kind of gives you another tool. You can have a theory, and then you have some equations. You can run a simulation of those equations, and you can see if it agrees with what you saw, or vice versa. Again, you can kind of reverse engineer things as well. So like in engineering applications, where the theorist may be like the designer of a car, and then the experiments might be in a wind tunnel, that would be astronomy. So it kind of helps to build the gap here. And so what kind of things might we be dealing with? And again, not an exhaustive list, but I just wanted to point out these four in particular. So radiation is pretty much everywhere, and it's not great. It's kind of, well, when I say not great, I mean humans wouldn't really want to be near any of this stuff. There are some nasty things, like, again, I said, extreme environments that we wouldn't want to be in the way of. But this is also a tool that physicists can use. They might study the radiation of something to try and infer valuable information about it. And then there's fluid dynamics, and this was surprising to me when I very, very first got into this subject, when I started learning about it, that the fluid model is such a powerful model, and it's used extensively throughout astrophysics, because at the end of the day, what we're dealing with in pretty much, well, in all of the applications that I mentioned to you before, is the movement of matter, how stuff moves, or perhaps more accurately, how things flow. right? So the fluid model becomes extremely useful here, okay? And we're going to talk a lot about fluid dynamics today, in fact. And then magnetohydrodynamics, which I've included separately to fluids, but this is essentially crucial as well, because there are very strong magnetic fields in space, and you can't ignore them, and you need to find a way to model the interaction of how this matter moves in the presence of a magnetic field. And then the final one that I put up here is relativity. And in pretty much all high energy astrophysical applications, relativity becomes important in some one way or another. And again, we'll get to that later, but I just wanted to point those four out off the bat. Okay. So the first thing that people ask me when I talk about fluid mechanics in space is they wonder whether fluids actually work, whether there is enough gas or plasma or something present to actually use the fluid model. So I thought I would clear that up straight away and say the answer is yes and no. It really depends what you're looking at. But in this case, we're going to use continuum mechanics. And if we look at the box on the right-hand side, this will be considered like a fluid element. And someone's singing.
I request everyone in the audience to please mute yourself. So, Jamie, if you give me 1 second, I will try to mute everyone and then you try to unmute.
Okay. All right. I'm unmuted.
Sorry about that.
Yeah, no problem. It happens. So I'll start again on this one. So okay. Thank you, Salim. So statistical or continuum mechanics. So in space, we know that you can't breathe. So people often assume that how could a fluid be present, and is this even possible? The long story short, yes, it is certainly possible. And just to clarify what we mean by continuum mechanics, so if we
I'm going to try one thing, Jamie, if that's
Okay.
fine with you. Again, really sorry about that.
It's all right.
Okay, I think so now people cannot unmute. I hope that.
Okay, let's see. I'm sure we'll find out in a minute again. Okay, so where was I? All right, a fluid element. So let's consider this box. Okay, the question is if we choose a box, or a random box in space, and is there enough gas present so that we can fill up that box and describe everything as one? So everything in this box, say, has the same pressure. And can you find out who it is and kick him out?
Yeah, I'm looking for that actually.
Okay.
Sorry about that.
I really want to get past this slide because there's more interesting things to come.
Yeah.
Okay, I'm just going to try again. So, can we model the fluid as a continuum? The answer is yes, and for the rest of this talk, we're going to assume that we can. Okay. So, perhaps when you were introduced to fluid mechanics, you heard of this Knudsen number, and it's essentially basically tells you whether you can use this continuum hypothesis, and it's related to the mean free path of the individual fluid particles, and there's the ratio of that and then some characteristic length scale, and if that number is low enough, then we can assume yes, we can treat this fluid model. And what it means is that we don't have to track each fluid particle individually. Okay, So this makes things a lot easier. So if you've taken a fluid mechanics course, a lot of the fluids that you learned there are applicable to space as well. Okay, I'm going to move on again to magnetohydrodynamics, a bit of a mouthful, which is we'll just call MHD from now on. And I've put the Maxwell equations on the right-hand side, and I'm not going to describe them in any detail, but I just wanted to point them out in case you hadn't seen them before. But it's a set of 4 equations that essentially govern the relationship between electric fields and magnetic fields. And if you have something like a plasma, like exists in the sun, and in fact exists in a whole bunch of astrophysics applications, MHD is a very powerful tool to describe the behavior of that phenomenon. And essentially it works like you have your fluid equations like the Navier-Stokes, and then you have your Maxwell equations, and you smush them together, and then you have a set of equations that describes the movement of an electrically conducting fluid. Okay, and this is also relevant for non-astrophysics stuff. So I put here an example of a tokamak, which is a big engineering challenge to try and get nuclear fusion going, and they need to use MHD a lot need to use MHD simulation, to try and figure that out. So it's very important outside of astrophysics as well. And the next point is relativity. And relativity comes in 2 forms, okay? And we have friendly relativity, or I think friendly relativity, which is special relativity, and we have scary general relativity, which is really hard. Like it's a tough subject to study. And general relativity is relevant when we, for example, have a very high density object like a neutron star or a black hole. And it can be summarized in this nice quote by John Wheeler, which perhaps sounds simple, but actually there's a lot of complexity hiding within there, which is just space-time tells matter how to move. So the fabric of space-time tells things how to move, and matter also tells space-time how to curve. So you can see in this picture how in the center we have, let's say it's the sun. It's something much bigger than the Earth, and is bending space-time a lot more. And we have like a planet, and it's orbiting around the sun, and you can see that it dents space-time a little bit, but not as much as the big one, and that's because it doesn't have as much mass. And this relationship between space-time and matter is described through the Einstein field equations, which I've put at the bottom for your reference. They perhaps don't look so scary, just written like that, but try to do something with them, and yeah, like you get a headache quite quickly. And then there's special relativity on the other side, which is more what we're going to be focusing on today. And there are 2 postulates of relativity. One is that the laws of physics are the same in every inertial reference frame, so every non-accelerating reference frame, and also that the speed of light is constant everywhere. So nothing can travel faster than the speed of light, which is often denoted as c. And as someone's already asked a question about time dilation, these two topics are important: length contraction and time dilation. And the way I like to visualize this is by looking at this light cone, which I've put here. And what we do is we imagine that we are at the very center of it, where it says observer. And if we go up, we move forward in time, and if we move across, we move through space, right? And if you travel exactly along the line of the cone, that means you're traveling at the speed of light, okay? So if you're traveling, let's say, at the speed of light, and you move up to where it says future light cone, so you kind of move just over halfway up. And if somebody else travels, let's say, a bit slower, but we travel for the same amount of time, it's like we might be at the same time, but we've been traveling for the same amount of time, but we've moved, but we're in a completely different place, which perhaps seems intuitive. Or alternatively, we might be at the same place, but at different times. And this is where relativity becomes quite fascinating. And I think everything I learn in science is kind of, nothing has kind of surprised me as much as special relativity. So everything is relative, and what it means is that your frame of reference is very important. Where you're observing from something from, it matters. And what you need to do when you incorporate this into an astrophysics model is you need to take that into account and make sure that everybody agrees on what it is we're looking at. Okay, so having said a little bit about these multiphysics topics, we'll jump straight into an example, and one of my favorite ones, which is astrophysical jets. And just to avoid any awkwardness, I've had some awkward conversations before where somebody didn't quite knew what I mean, and as this is a very audience, I think I'll just clarify this now. So by jet, we don't mean a fighter jet. Somebody thought I was talking about Star Wars and things flying around in space, but actually what I mean is this kind of jet that's the exhaust jet of the aircraft, and it's quite a beautiful image. And yes, these things exist in space, and they are mind-boggling, and they are a fluid dynamics problem at their very core. And there's some interesting stuff that goes on in here. So just looking at this jet, you can see that there are some white spots that appear, and that is some complex interaction where they're called Mach diamonds, and it's internal shock waves reflecting and creating this beautiful structure. And you may wonder whether such things will exist in space as well, and perhaps, well, we'll come to see. So what are these jets like? This is galaxy M87, and it's in the Sagittarius constellation, I believe. And it's kind of became famous recently because of the photo of a black hole, and that I've put in the slide there. And so that same galaxy that they found the black hole at its core and took a picture of it, that also has a jet screaming out of it, and it roars out at about 70-80% the speed of light in places. Is extremely fast, and it's extremely long, about 5,000 light years in length. This thing is just shooting through space. Like, the mind can't even quite grasp the time and the length scales involved in these things. But yes, oh wow, it is very cool. So how can we model this? How can we use fluid mechanics, for example, to model this? Because I've said that this is a fluid dynamics problem at its core. Well, let's start with the Euler equations. And most of you have probably come across this in a basic course of fluid dynamics. So let's start there. We've assumed that the continuum hypothesis is valid, as I struggled to get through that slide on that. So we'll assume. And we'll also assume, because this is very big, very fast, we'll say that things like viscosity and heat conduction are negligible. But unfortunately, if you try to model something like this with these equations, it's not going to work, I'm afraid, because the flow is too fast and you're not going to capture the correct physics. There's not enough multiphysics in these basic fluid equations for you to be able to describe it. So what do we need to do? Well, let's put special relativity in there, and let's get something like this. And I've written it in a slightly different way. It's a bit easier. But this is a system of conservation laws. So the top equation here, du by dt. Now, u are our conserved variables. So mass, momentum, energy, exactly like what we had before in the Euler equations. And they move according to a flux F, which is given over on the right-hand side there. And this is kind of a compact form. So I is x, y, and z in 3 dimensions. Excuse me. And we have some additional terms at the bottom. So we have this W, which is a Lorentz factor, and that is something that comes into relativity, and it's a factor that basically says how much space and length and time are changed. Okay, and then we have H, enthalpy, P is pressure. We're going to use a simplified equation of state. We're not going to go into that. And we have this velocity here. And you'll often see in relativity people talk about the Fore velocity. And the reason why they do that is because space and time are sort of elegantly intertwined. We have four components of the velocity, where the first one represents time, and then we have x, y, and z. Okay, so actually these equations, they don't look a million miles different from the Euler equations. They kind of do the same thing, and it's fortunate for us that we can write them as a system of conservation laws. But we still have to add some more stuff, as you can probably see that it's coming, because to correctly describe a relativistic jet like this, we need to use MHD. So enter some extra stuff. And you see we have these B's everywhere that are talking about basically the magnetism involved. And very quickly, we've gone from the Euler equations, which were sort of friendly and familiar, to this system which has become a little bit scary, okay? But there is good news, and the good news is that we can solve this, and people have been solving this numerically for quite a while now. And what they're able to then do with this is reproduce images like this. So using those exact equations that I just showed you on the previous slide, this is a simulation of a relativistic jet. It doesn't quite look exactly like the Messier 87 like I showed you, because this is a different example. But we have some similar characteristics. We have something going on sort of in the core, about 75% of the way up. I just lost control. Hey, give it back. Someone messing with me today. Okay, so we have this simulation of a jet, and okay, someone keeps taking my control away from me. Please don't do that. Okay. So yeah, like we can solve these equations using a series of numerical methods, and we can reproduce something like a jet, okay? And another example here, which is a little bit more similar to Messier 87, which I showed you. And here we can see some more complex interactions, both inside of the jet, like what we saw at the exhaust of the fighter, and also around the outside. We see lots of instabilities occurring, and we can also see, especially at later times, so from top left to top right, this is the jet moving forward in time, and we can also see some nice shock waves appearing around the front of the jet as well. And again, this is done by solving the simulation, solving the equations which I just showed you, which people are relatively good at now. So you can see this paper is from 1997. And so we've been doing it a little while, so it's okay. We're happy with this. So moving on, what you can do if you were an astrophysicist, perhaps, is you might take these simulations and you might compare them to something else. So I'm not saying that these are good comparisons, but I'm just trying to give an example here. So the first one is a radio map. So this is another jet called Cygnus A, and it's obtained through radio astronomy. So they're using those antennas that I showed at the beginning. They're scanning the sky, and they've produced this map using radio waves. And then also you can simulate a radio map using some radiation code or something, and you can see that there are these hot spots appearing, which may correspond to these internal Mach reflections, which I mentioned. And you can just build up a picture and do an investigation like this. It's something that astrophysicists might want to do, and how they might want to use simulations to help them. And one of the ways simulation and theory really came together to help the progress with relativistic jets is people wondered why these jets weren't so unstable. If I just quickly jump back 2 slides, so at later times with this jet, we can see some complex interaction here, and the fluid motion is kind of curling up. And why is it that, because these things are going so fast, why doesn't this instability occur, the Kelvin-Helmholtz instability, which happens when you have a shear layer between 2 fluids or same fluid with different density, just like we have on the outer side of the jet? Why is it that this instability doesn't occur and deteriorate the jet and it breaks up, which is something which we see when we have these kind of jets on Earth? Like, why doesn't that happen? So the theorists, they did their thing, they did some theory, and they said, oh, well, we think it's because of relativity. And it was actually proven by a simulation that, yes, these jets are stable and are able to extend for such a long time because this instability is actually suppressed by relativity. So because the relativistic effects are so strong, this instability is kind of damped out a little bit, and the jet can propagate for a very long period of time. And this is supposed to be a video, but for some reason this video does not work when PowerPoint is shared through Teams. So it's a simulation of the Kelvin-Helmholtz instability. Okay. So let's go on to the actual tools. What's going on underneath the hood when we're trying to solve these equations? And I've called it CFD for high energy astrophysics because CFD is essentially the main kind of ingredient. It's CFD with extra stuff, right? It's CFD with relativity or with magnetic fields, but CFD is at its very core. And in particular, kind of the state of the art that's used for high energy astrophysics nowadays is this thing called high resolution shock capturing framework. And I pretty much all of the high energy astrophysics codes are built using this methodology. And it's very necessary because incompressible flow is not really a thing here. Everything is compressible, and we're very likely to encounter shock waves in astrophysical applications. So we need to make sure that we can capture this flow correctly, right? And I want to avoid using jargon here as much as possible, but this is what's called a Godunov type methodology, and I will come on a little bit more to what that means later. But essentially, a Godunov type methodology relies on the solution to what's called a Riemann problem, which I'm going to come to in a second, okay? And if you're familiar with these kind of framework in the non-relativistic or non-MHD sense, I've put a flow chart of how a typical code might look, and it may surprise you to see that, okay, it's pretty much the same as what you would have for fluid dynamics, normal fluid dynamics applications. Even though it's for astrophysics, it's generally the same kind of deal. We're following the same kind of pattern to solve these equations, even though we have all of this extra stuff in there, okay? So this Riemann problem that I mentioned, I feel like is best illustrated through an example, and I will try to make this as clear as possible, but it can be sometimes a challenging subject. So if we consider this gray box in the top, and it's split in half by a membrane, okay, and on the left hand side we can define our density, velocity, and pressure, and on the right hand side we can do the same. And let's just assume that we have low density, low pressure on the left, high density, high pressure on the right. And then we release the membrane, and some fluid dynamics stuff is going to happen in there. And it may be possible that there is a shock wave that forms and it propagates to the left, okay? So this is just, it's not immediately obvious to you. It doesn't matter. Like, let's just assume that is the case for a second. And depending on how you would define the density, pressure, velocity on either side of this membrane, different flow patterns might emerge. So shock waves, rarefaction waves, all of these different sort of things could occur. And on the right-hand side, we have how this flow profile may look. So this graph is the density across this shock tube, it's called. And you see we have a high density on the left and a low density on the right. And underneath it, I've drawn this strange thing, which is called a Riemann fan. And the Riemann fan has time on the y-axis and space on the x-axis. And what it can show us, in fact, actually it's wrong. I did it wrong. So S and R should be the wrong way around. It should be the other way around. Actually, we have a left-going rarefaction wave and a right-going shock wave. So here is a shock wave. This should be S on the right. I think you can't see my mouse, but on the right we should have S instead of R, and on the left we should have R instead of S. So we have a shock wave moving to the right and a rarefaction wave moving to the left. So at the very origin of this, at time t equals 0, and as we move forward, as the flow develops, our say shock wave, it moves to the right as time, and a rarefaction wave moves to the left over time. Okay, that's pretty much all I want to show you from that. Somebody is not my friend today. Abhishek, my presentation is gone, right?
It's still being shown, like your screen is being shown right now.
What do you see?
Yeah, I see your PowerPoint.
Am I on the first slide?
Yes.
Okay, all right. Let's do some skippies then. Now maybe this thing works. Yeah, so my video of the Kelvin-Helmholtz simulation works now. So there we can see how Kelvin-Helmholtz develops, just to backtrack to there. Anyway, let's go forward. Where were we? Okay, so we talked about this Riemann problem. No worries about it too much for now. It's kind of sometimes it can be something hard to get your head around, but I did want to mention it because it is so important, and I'm going to come back to it a bit later. But bear in mind, this is called a global Riemann problem. So this is a shock tube. This is how a shock wave is moving through a tube, or a rarefaction wave is moving. Okay. Moving on. How do we solve that equation then? Like how do we predict the flow moves? Well, in this case, we'll talk about the finite volume method. So the beauty of having the continuum hypothesis valid is it means that we can use grid-based techniques, and that's what we're going to consider in this case. So let's say we're using finite volume, and we have this grid, we have these squares, right? And this black square in the middle, we're interested in evaluating what goes on here numerically, and we want to follow the conservation laws, conservation of mass, conservation of energy. And one of the things that this method permits us is that we can say, okay, what goes in must come out the other side. You know, we can automatically satisfy this conservation law using finite volume. Okay, so yeah, here we have it here with the equations. So on the left we have that conservation law that we discussed, well, what I showed you earlier with the conserved variables u move according to the fluxes. And then on the right, we can reduce that to an ODE instead of a PDE, and we can write it in terms of these fluxes F. So we have a flux, say, on one side and a flux on the other. And all we need to do really is we need to calculate the flux of fluid coming in and going out again, or vice versa. And then we can use that information to advance our solution forward in time and run a simulation, okay? So this is where the Riemann problem comes back into it. So I said to you before that we have a tube, and on either side of the tube we had some gas with this property and other side this property. What we now do is we now take that general idea and we don't just consider it for the whole domain, but we consider it at every single cell. So every single computational cell, we are now going to solve the Riemann problem. And the Riemann problem has these two initial states. And the beautiful thing is that it could be a discontinuity. Okay, so let's say we have a shock wave where there is a sudden change in density. So on one side there's a high density, the other side there's a low, just like what we saw before. And the Riemann problem is it deals with that directly. Like, it's okay to have discontinuities, and translate that back to fluid mechanics with shock waves and things like that. It means that if we solve the local Riemann problem at every cell face, then we automatically can detect and capture shock waves. Okay, so this is what a Goodenough type method is. It solves the Riemann problem at every single cell face, and it's proven incredibly successful. Like, it's a really handy thing to have in your arsenal. And in astrophysics especially, pretty much every fluid dynamics based code will have this at its center. It's considered like this kind of philosophy is what would be the standard, let's say. And just like how we had this Riemann fan before, we do it at every cell face. So this is where it can get a bit confusing between the global Riemann problem and the local one. But we use these things called Riemann solvers at each cell face, and it's essentially a method to solve the Riemann problem, and it's built upon these conditions called the Rankine-Ugonoy jump conditions, which describe how the state variables change across a shock wave. And I haven't included all of the formulas here because it's a bit unnecessary, but this SL and this SR that we see, they are what's known as the wave speeds. Okay, and they come from the eigenvalues. We can compute the wave speeds at each point in space using the eigenvalues of the original system. Unfortunately for us, the system that I showed you before, it's a hyperbolic system, which means we always have real and distinct eigenvalues. And this is, again, how we can make use of this high-resolution shock capturing framework in astrophysics, is because of these mathematical properties of the equations. So I won't say too much more about that and try to describe this thing. But when you use these Riemann solvers, sometimes you want, one thing I should say is that these wave speeds, this is just for hydrodynamics, but if you're considering MHD, you would have different waves. You would have more. So there would be Alfvén waves and magnetosonic waves, and the whole notion of the Riemann problem becomes slightly more complex. But I wanted to just try to keep it a little bit simple here today. So what we want to do is design Riemann solvers to evaluate this flux, and we want to be clever, right? We want our work to be accurate, but sometimes, you know, you can be too clever, and what can happen is your solution actually deteriorates as you use more accurate techniques, which kind of sounds a little bit counterintuitive. And one of the problems that you might have with this is called the Carbuncle problem. Okay, so in this example that I've put up here, and this is not from an astrophysical example, this is from a normal aerospace application. So we have a re-entry capsule, this artist impression here, and there's a bow shock that will be formed in front of the capsule as it enters. And here you can see in the Schlierian image this sort of circular line in front of the blunt body, and it's a little way off into the front, but it's a nice kind of curve. Okay, and this is what it looks like in real life. But if you use some of the most sophisticated techniques, you have what you see in this figure A here, and these are pressure contours, and we have this solid body, and we have the flow coming into it at 8 times the speed of sound. And look at that, it's kind of like jetting out, which is really odd. Like, this is not what we expect. And this is the carbuncle problem, and it's an instability, but it's completely non-physical, and it just ruins your simulations. And if you've taken an introductory course in fluid dynamics and you use some simple numerical methods, and you use some simple numerical scheme, you find that, okay, maybe it's not as accurate, but it pretty much always works. But as you get more complex, maybe you start to see wiggles in your solution, and things become a little bit more unstable. It's kind of like what's going on here, and that we're like I say, we're being too clever, and our solution is deteriorating. And the reason why this happens is because in these sophisticated techniques where we're trying to capture more of the physics, perturbations in this case, perturbations in the pressure field, they grow and they eventually distort the flow. They completely ruin it. So this is where the instability comes from. It's just something is not quite right somewhere, and then that just grows, and then it just messes everything up. Okay, so if you are designing an astrophysics code, this is something you need to be aware of. We need to capture shock waves well, but you have to be careful. Sometimes things don't go right. And I put an example here of a simulation I did with a jet, slightly different again to the ones you saw. And again, this is a carbuncle appearing at the front of the jet. You see it's started to kind of distort the head of the jet, and there's this tip jetting outwards. And this again is the carbuncle problem. And it shouldn't happen. Like we shouldn't have it, okay? And it's because I'm using a Riemann solver called the HLLC Riemann solver, which maybe some of you are familiar with this. And this is kind of let's say it's a good Riemann solver. It's very accurate, okay? But due to its how sophisticated it is susceptible to this issue. And so what can we do about this? Well, we can try and be clever and combine the use of two Riemann solvers. And so in this formula here, we have this psi HLL, psi HLLC, and we have a strategy where if these are our cells on the right, depending on the direction of the shock wave, we can use a Riemann solver which we know will give us stable results in the direction normal to a shock, and then everywhere else we can use the better Riemann solver. So it's not just switching one on and one off. It's about actually adaptively moving how we calculate this flux depending on the direction of the flow. And it's one solution, and if you apply it, you get something that looks a bit more reasonable, where we have a carbuncle-free solution. But before, we weren't getting as much detail in the jet, but now we're getting more detail because we're able to use the good Riemann solver and the more robust Riemann solver to kind of get the best of both worlds and achieve a more preferential solution. But this does come at the cost of the computational expense. So it does take a lot longer, and it's by no means an optimal solution. But I just wanted to highlight to you today that this carbuncle problem is a challenge, okay? So moving on, another big challenge that we face in this world of numerical relativity and high energy astrophysics, CFD, is what's known as primitive variable recovery. And most of you maybe didn't give too much thought to this before, but when we solve the classical Euler equations, the mass term, we evolve the mass in time. Well, mass is just rho, and the momentum is rho times u, okay? And because we evolve mass, momentum, and energy over time, we need to recover what we call the primitive variables, which are velocity, density, pressure. These are the things we're interested in. No one asks, what is the momentum at this point? No, you want to know what is the pressure here, what is the density. So we need to recover this from the actual conserved variables which we evolve. And in the classical case, it's easy. It's really just simple algebra. Divide the momentum by your mass term rho, and you've got the velocity, and then you can just get everything else. Like nothing complicated there. But what is really a challenge then for relativistic flows, more so for relativistic MHD, is that there is not a direct mapping between conserved and primitive variables. So when you're designing a code to solve these equations, you need to be very careful, because you have to use a root finding algorithm, basically. An example might be the Newton-Raphson, and you have to do some algebra, and then you have to solve this equation and essentially fathom what are my primitive variables. Normally what you do is you solve for the pressure. So you try to find the pressure first, and you iterate and iterate until, okay, I'm happy with the pressure, and then you gradually can find everything else. But because you're having to use a numerical method to do this, it's naturally a source of error in the code. And there's not one standard way to do it. So some methods that you might use that you see in papers, they might fail in extreme circumstances. Like if it's a really high Mach number flow, or it's a very relativity, very, very close to the speed of light, for example, it might fail, and you need to be careful of this. And also what it means is that if you want to include a more sophisticated equation of state to capture more physics, this is kind of an obstacle that you have to overcome, because to recover these primitive variables, you need knowledge of the equation of state. And the more complicated your equation of state is, perhaps the more difficult it is to recover the primitive variables. So this is sort of a big challenge. It's relatively easy to overcome, but when you're designing the codes, you need to be very careful of it. Okay, next, the Big Bang. This is, I wanted to finish actually with this example, because people don't talk about it too much, and it's a thing called the quark-gluon plasma. So just after the Big Bang, this state of matter existed called the quark-gluon plasma. The universe was essentially it's called a soup, actually. They call it a QGP soup, okay? And it's an interesting state of matter. And it's one of the things that we can actually study experimentally, and they do so at facilities such as CERN and RHIC, the Relativistic Heavy Ion Collider. And what they do is, just like that name suggests, is they accelerate these heavy ions around and around and around in circles, and then they smash them together, and they can create this state of matter called the quark-gluon plasma. And because these things are heavy ions are accelerated to almost the speed of light, you need a relativistic treatment to describe this quark-gluon plasma just after it's collided. And it only lasts for, as you can see at the bottom, about 10 to the minus 23 seconds. But there is sufficient time where it is in what we call a hydrodynamic state, so it can be modeled as a fluid. Okay, and when they first made the QGP, they said it was the most perfect fluid they've ever seen. And what they mean by that is that it doesn't have any viscosity or anything like that. And then they figured out, actually, no, it does have some viscosity, because it's kind of impossible to not actually have any viscosity whatsoever. And then this kind of gave birth to this whole topic of how do you model viscosity and heat conduction with relativity. And it may seem like actually it's not a big deal, whatever, you just stick a source term on the end of your governing equations, and there you go, job done. But viscosity and heat conduction do not play by the same rules as they do on more earthly applications, okay? So Professor Niels Anderson from Southampton, he gave a talk at Cambridge last year, and he was mainly talking about this in the context of black holes and things like that. And he said it's a massive problem that people don't like to talk about. And he then went on to say that this is either because people don't understand it, or because they don't know that it's actually a problem, okay? So now you know it is a problem, okay? Whether we understand it or not is a whole nother ballgame. It's quite a challenging subject. But again, to continue on what Niels Anderson said, he said that if you take the standard theories of viscosity and heat conduction, or let's just take heat conduction for the example, heat dissipation, and you apply it in the relativistic context, it will give you a theory, somehow it will give you a theory that predicts that a glass of water at room temperature will explode. Okay, so a 4-year-old can tell you that a glass of water at room temperature is not going to explode. It doesn't make sense. But when you try to combine the classical theory of viscosity in the context of relativity, it doesn't work. It's garbage. Like we can't do anything useful with it. Okay. And so what can we do? Well, this is a good question. It's still kind of under debate, actually. There's no universal agreement for how to correctly model viscosity and heat dissipation in the context of relativity, but we have an idea of what we can do. And it all sort of stems back to this paper that I put down at the bottom from 1979 by two Cambridge mathematicians, Israel and Stewart. And this theory is known as Israel-Stewart theory now. So if you scan the literature, search for Israel-Stewart theory, this is kind of what most people are using to try and describe this. And it's tricky. It's not an easy subject at all. But basically, if you use the standard theory, it says that if I heat something to my left, and then I heat it over to my right or over the other side of the room, you can feel the effect instantaneously. Heat travels instantaneously, which doesn't happen. It's a violation of special relativity in some cases. This is what where the problems lie, and so you need to slow it down essentially, and you need to incorporate lots of extra physics into the model. And what I've put here is what this T is like a stress tensor. And the first stress tensor is what you would need to describe with no viscosity and heat conduction. And then the one underneath, this Q is for the heat, and this tau is for shear and bulk viscosity. And then you have to derive your equations using that. And what you find is that you go from your normal relativistic hydrodynamic equations to this much more complicated structure we have here. And what's interesting to note is that in the conserved variables, du by dt, we have heat terms and we have viscosity terms. So we have to differentiate that with respect to time, which is something that you don't see in the classical case. And then of course it all appears in the flux. But in addition to that as well, you need to solve these telegrapher equations down at the bottom. And you can see that there's another term, tau 0, tau 1, tau 2. And what these are relaxation times. So if I heat something up, if I heat this book up, how long is it going to take for this book to basically calm down and go back to its original temperature? That's like a relaxation time. And then the next difficult bit is how do you get that relaxation time? Because it depends on the fluid itself. And this is where kinetic theory comes in. And if you've ever tried to combine continuum mechanics and kinetic theory, well done to you. It's I'm sure there are prizes available for you. But this is kind of a way that these things merge together, because to understand the relaxation time, you need to go into the kinetic theory and the thermodynamic properties of a unique fluid. And then you need to feed that into these continuum equations, and it's really difficult. So we don't do it at the moment. We kind of stop there. And Israel and Stewart, they gave some general expressions of how you can come up with these relaxation times, and we do what we can with it. But it's a lot of extra work. So the flow chart that I showed you before without dissipation and then with, you can see that there's a lot of extra steps that you need to do, and you need to do all of this once per time step. Okay, and from my experience, it made my code, if let's say I ran a simulation without dissipation and it took, let's say on a single processor or whatever, and it took an hour. With dissipation, it would probably take maybe an hour and 45 minutes, something like that. Like it's kind of a lot of extra work to do. All right. So it's very necessary for these quark-gluon plasma applications. But to return to our friend, the Kelvin-Helmholtz instability, on the left I run a simulation here without any viscosity, and it's a relativistic application. And you can see that these funny structures are emerging, and perhaps it looks quite cool. But then I run it with viscosity, and they don't appear. And it kind of makes sense. Okay, with viscosity, we're dampening out these small perturbations that grow. But there's something much deeper going on here, because this simulation without viscosity, I've used some of the most sophisticated methods that I had available to me, and they produce this flow profile, which, based on the initial conditions that I needed for the instability, we actually know that it's non-physical. Like, it shouldn't happen. Like, these methods, even though they're really good without viscosity, like they solve the equations really well for shock waves and stuff, in the case of this shear layer, it's wrong. Like, it is wrong. But when we include viscosity, and in this case it's actually only a small amount, we get rid of them. And it's kind of opened up this new conversation where, although we have these very accurate methods, it's like with the carbuncle problem, are we shooting ourselves in the foot again? Like, are we being so accurate that we're actually wrong? Or do we need to include more physics? And my argument would be, yes, we need to include more physics if you want high fidelity numerical simulations. So including viscosity is not just important for things like the quark-gluon plasma, but I think it's just important for fluid dynamics studies in the context of relativity in general. Perhaps that's kind of a wishy-washy explanation, but I'm happy to discuss this more if you'd like. So that kind of is all I have for you today. So thanks very much for listening to me. I leave some takeaway messages there, like feel free to browse them, and perhaps you can use them to think of some questions or something. But thanks for listening to me, and yeah, happy to talk to you more.
For that, sorry. Okay. Thank you for that. And it's really interesting. I don't know why my voice. Can you hear?
I can hear you. Yeah, no worries.
Okay. So yeah, thank you so much for that. It was really amazing. Very interesting. After a lot of time, I think so. I was into like so much focus on the presentation that I was like, it was attending a lecture, and it was really great. Because there's a lot of issues that you pointed out that we see in CFD realm also currently, like me dealing with like incompressible flow and all that. We do see some of the issues, and there's always this, whenever viscosity comes into play, there's always something very like you just try to do something there, and which might not be mathematically very rigorous. So that's very important to understand also. But it's great to see that even in compressible and astrophysics applications, these things become very much relevant and very much important to think about. And I think so this is where numerical challenge in like developing methods always lie, especially when there's like shock waves and everything. People now are trying to use something as at least what we are interested in, we are trying to use something as discontinuous Galerkin methods for those kind of things. And I would open the platform for the audience to ask questions, but I do have one question before we jump in. What is the usual discretization method that is taken in when you're dealing with something in astrophysics realm?
You mean like the meshing strategy?
No, more on discretization as in the method of like finite difference or finite element.
Okay. So I think that what is definitely most popular is finite volume. Like I would probably say that, well, yeah, let's say 80%, 70-80% of most codes are finite volume. But as you pointed out, discontinuous Galecki methods are beginning to become popular. But from my understanding is that they don't always work out of the box like finite volume do. They're a bit tricky, and you need to do some extra work. So there are definitely some papers that are applying it to the relativistic hydrodynamics and MHD as well. So it's coming, like the research is there and it's being done. And I imagine that more and more people are going to adopt this in future for sure. Yeah.
Yep. Because in these cases, like there are places where I saw, I felt like you need like having higher order methods would help a lot. And that's why when you want to deal with higher order, either you can go to finite difference, which is not very, I mean, I've not dealt with these kind of flows yet or these kind of situation, but finite difference doesn't seem very apparent in these cases. Like it would be finite volume, but it does not provide higher order. Higher order capability that finite element, and that's why that was interesting. Great. Okay, so let's dwell into questions. The first question, I'm just trying to see. Where's the first question? Okay, so the first question is, how different and better is gravitational wave astronomy compared to the existing techniques?
The gravitational wave astronomy, it's designed for gravitational waves. It's not for looking at anything else really apart from gravitational waves. So it's different in the sense that it sort of has one purpose. I think that's what they mean, right? Maybe I can find the question, but yeah, it's different because it uses completely different technology to measure essentially ripples in the fabric of space-time, which of course you can't do with a telescope, and you can't do it by looking at radio waves or something like that. So it's a very bespoke piece of engineering designed for that exact purpose. Yeah. You're muted, Abhishek.
Oh, sorry. Thank you for that, Jamie. So the same person, I think, so asked that which one of the two is more difficult to comprehend? General relativity, I think so that's what he meant by GR, or quantum mechanics.
I don't know. I guess it depends what side of the bed you wake up that morning. But I mean, for me, I haven't really dealt with quantum mechanics before. I read a little bit, but I guess that's kind of a personal matter. Which one you enjoy the most, which one you find most interesting. Certainly, they're both fascinating, but yeah, they're both very challenging topics in themselves. So yeah, I guess I leave that question back to you. Or ask you which one you might find.
No, I'm not the expert in either of those, so I'm not going to comment. But I do have one question, for one follow-up from my end, which I think so will be very useful for the audience also. So you finished your PhD in dealing with these kind of things, and I am assuming that you also dealt with high performance computing, and Jesus can also like jump in if he wants to give some views on that. But where do you see quantum computing playing a role in this case? Like when you have such situations where you really require high computational power, according to your experience, what do you think is the future that quantum computing holds in this area of multiphysics, I would say?
Well, I think like all of the other subjects that we saw throughout this lecture series, there's always more what we want to do, like with including this. If you want to include relativity, MHD, viscosity, all of this is adding up to what is quite a nice model, but it gets really pricey if you want to solve it, you know, like especially in 3D. So like again, I mean, I don't know anything really about quantum computing, but if it speeds things up, that's great, you know, like yeah, I think that's all I could really comment on that, but yeah. So I definitely see it
Yeah.
being very important. Yeah.
Yeah, thank you. Jesus, your thoughts on that?
I don't have to add anything on that. I mean, I think Dr. Townsend really summed it up, especially when you add more variables to the equations and you start adding up more models. You require more time, and if quantum computing can breach that problem, it will be a very good help for us, the CFD multiphysics engineers, that we are fascinated about this field. Thank you.
Yeah, definitely. I mean, that's the hope. That's the vision that we saw, that there is definitely a challenge, and if we can really get to that part where when we have larger degree of freedom, and we can solve these kind of systems much more faster. That's the hope. That's the hope, and that's the vision that we are trying to go ahead with. But thank you for that. So back to the questions from the audience. Uh, The one question that we have is, by astronomical jets, as in jets from quasars or neutron stars. I think so. It might be the part of your presentation.
Yeah, exactly. So in the example that I showed you, there was a black hole at the center, but yeah, quasars and neutron stars, you also you find jets in these situations also, or not always. It's not a guarantee, but yeah, these are the kind of environments that you might find them. I can't elaborate in tremendous detail, but yes, you are correct. Yeah, yeah. You're muted again. Yeah.
Thank you. So on slide 14, you showed, I think so, some picture. Is there any turbulence model that was used on that?
No, we haven't got to that stage for relativistic simulations. Partly, well, as I was talking about how difficult viscosity is, this is kind of this is a big challenge which is related to turbulence modeling. So the short answer is no. It's a DNS simulation, if you will. Like there's no turbulence modeling going on whatsoever, and I'm not sure how useful a turbulence model would be. I haven't given it a whole lot of thought, to be honest, but perhaps I'll have a think. But yeah, in this case, there's no turbulence modeling at all. Yeah.
Okay, great. Thank you for that. That was some question that even popped up in my mind. So thank you for asking that question. So next question is, in astrophysics community, are people interested? First option is FSI problems. Number two is multi-phase problems. Number three is phase transition problems.
FSI, not in the traditional sense. I would assume people are certainly interested in what happens when things interact. Like, for example, if you have a cloud of gas in space and a shock wave hits it, it's called a shock cloud interaction, we call it. Things like that, but it's not really a structure, but things hitting into each other, like it does happen, but not in the typical FSI case. Multi-phase, yes. It's a very specialist subject, and this professor I mentioned, Professor Niels Andersen, he works on this, and I believe they use it a lot for neutron stars. I don't know too much about it, but multi-phase is definitely there, but it's not. I'm trying to think where else I've seen it. I mean, it's there for sure, but it's quite a tricky thing, because If you have two fluids moving together, they each have their own world lines. So you have to, like, the reference frame that you use is very important. So do you use the reference frame of one fluid or the other? And like, it becomes kind of tricky, and the maths involved there is very difficult. But the group in Southampton are dealing with that, I'm pretty sure. And what was the third one? Sorry.
Phase transition problems.
Phase transitions? What do you mean by phase transition? Sorry.
So phase change. I think so. That's the person. Yeah, phase change.
Phase change. What change of what kind of phase?
I think so. The one that you mentioned. I mean, that the one that you initially mentioned, like the cloud, the shock hitting the cloud. That could be an example of a multi-phase problem or a phase transition, because I'm not sure. I mean, I'm just guessing here. Maybe.
Okay. I'm not sure either. Yeah.
Anirban, if you want to unmute yourself and ask the question, re-ask or like clarify that point so that Jamie can answer that better. Okay, so like phase change from like liquid to vapor. Is there a phenomena in astrophysics that you deal with?
I'm sure there must be somewhere along the line. Let me think a second. I'm not sure exactly. I can't think of a really specific example, but yeah, it must occur. But I've never really read a paper where they're discussing this deliberately. I tend not to read a lot about so much about the physics, and I normally read about the numerical methods. But I imagine so. Perhaps in the star formation, things like you said, a cloud shock interaction. I imagine it goes on there, yeah, but not 100% sure about that.
Okay.
Yeah.
Thank you for your views on that. The next question is, can the hypothetical micro black holes be simulated and eventually made using quantum computers?
I have no idea.
All right.
Not sure about that one. Sorry.
Okay. Okay, this is something. What difference would using a quantum computer make, if possible, of course, when simulating numerical code for, say, the Riemann problem? Would the stick up a relativistic term and terms like that be made easier because we can test for various values at the same time? That's a good question.
Stick up?
I mean, include the relativistic term. I think so. That's what the person meant.
I don't fully understand the question.
It's like quantum computing can, due to its potential of using like qubits, instead of doing everything like serially, let's say if you have something, when you take a problem and you do like a serial for loop in that, a quantum computer can do it parallelly, just like if you can think about like maybe GPU. So maybe that is what the person is trying to ask. Can you actually see that being a potential in this?
I mean, with the Riemann problem, yeah, because you have to do it absolutely everywhere. If you can do it more than once in different parts of the code, it's like what you would do if you parallelized it using MPI, then yeah, for sure. Perhaps where it would be even more useful is in the case of viscosity, actually, because you can do your regular part without viscosity, and then you could actually get the quantum computer maybe to calculate the viscous stuff at the same time, because all of those steps you need to do every time step. So yeah, maybe it would be really useful there, like splitting the algorithm up that way, because actually with viscosity things are happening at different time scales. So the viscous stuff obviously happens at the small scale, Whereas if you have like an example of a jet, it's very big, takes a long time for the flow to evolve, but the viscosity is still happening on the small scale. So that kind of disparity between the scales, perhaps quantum computing really could help out there. Yeah.
Okay, great. Thank you. Thank you for that. So, okay, this is asked. What are some of the unsolved problems related to astrophysics, something that is being actively researched right now?
Unsolved problems in astrophysics. Well, I'm not an astrophysicist, so I'm not sure I can speak to that very well. I think the immediate thing that immediately comes to mind is dark matter. What is it, and what is it, and what role does it play? I would say this is kind of one of the most perplexing things. A lot of stuff around gravitational waves as well, like testing Einstein's GR theory to its limit. What else? Well, I think the biggest unsolved problem probably dark matter. That's the first thing that comes to my mind. Yes, but I don't know much about this stuff. Yeah, it's out of my comfort zone.
Okay.
Yeah.
I mean, just to give add to that, I've been relatively very interested in something called as quantum turbulence. So with that, I think so falls under magnetohydrodynamics. And recently, I also got to know about that. It is not only something that you see in very nano or micro scales, but you also see in something as astrophysics happening. So I think so that is one of the problem by a professor from New York University, NYU. He is a Indian origin professor, and he started to look into it um, in 1916, 1970s. And that I think so falls under something which, like I said, in astrophysics. So there's a very good review paper by him um, in journal for fluid. Ruth can help me here if he's still there. There's a very famous journal, a review paper on fluid mechanics. I will just while
Annual
you
renew for fluids.
review of fluid. Yes, that journal. Thank you for that. So yeah, there is. If you see the 2016 edition, and I will put down the name of the professor in the chat.
Okay.
Couldn't remember, but that could be something which might be interested in astrophysics realm also. Okay, next question. And this is a question from Ruth. Could you go over why we can model astrophysics as continuum since at high altitudes we switch to molecular simulations?
Why can we? Well, it's because we not always we can. In places like the interstellar medium where the gas is very dispersed, and you wouldn't be able to use the continuum hypothesis there. But in the cases like the jet, when you're considering the bulk motion of the fluid, and in things like supernova, there is enough fluid particles there. Like it just is. You know, we're able to do it. We don't need to use rarefied gas theory or anything like that. It's kind of a fortunate thing, really, that we can use these tools. So yeah, I hope that answers.
Okay. Yeah. Another follow-up is I think on slide 15 there were snapshots of essentially the simulations of these pulses, and there were eddies that were forming.
Oh yeah.
Yeah, can you talk how those eddies form? Because are we talking still in the medium is still in the continuum realm? The medium through which the pulsars are, or I guess these jets are traveling through,
So
are they still in a continuum medium?
like the instabilities occurring around the outside of the jet?
Yes.
Yeah, well, I mean, I would imagine that initially they are because there's still a property of the jet, but as as like the instability grows and then perhaps deteriorates, a transition into turbulence, and then it's all going to fizzle out. If you really want to be super precise on that particular point, then yeah, the continuum hypothesis is most likely going to break down outside of it. But I've never seen anybody look in that much detail at these jets. But it's a good point actually that you raise, because yeah, if the surrounding gas that it's being ejected into in the interstellar medium is, let's say, where the continuum hypothesis is not valid, then as they interact at that boundary, yeah, something is going to go funny there, right? I think that's what you mean.
Yes,
but,
yes.
Yeah, but in the simulation that I showed you, that's not taken into account at all. It's just continuum hypothesis assumed everywhere. Yeah.
Right. Okay. Thank you.
Mm-hmm.
Okay, so the next question is, I'm not sure if it is related here, but personally, do you think chaos theory can model astrophysical jets and so on? Is chaos somewhere in there?
I'm not sure. I mean, I don't really know much about chaos theory, but I don't think that it would fly here. Yeah. Yeah.
Okay. This is another question, a rather naive question. While solving classical fluid problems, we assume that the stress tensor is symmetric. For problems in astrophysics, is it still the case?
Yes. If you're not having any, let me think what it looks like. Yeah. If you're not having any viscosity, and it would be symmetric, so you would have an isotropic pressure field. It is still the case, yes. It obviously looks different, but yes, it is still, yeah. But if you wanted to include anisotropic effects, then you would have to change that. But in the examples that I showed you, yeah, it's symmetric. Mm-hmm.
Okay. I think so. This is one of the last questions from this chat, and then Ruth can bring in few from YouTube if there's any. The first question, so there's like two parts to that question, and this person is from CS background, so the person is having very specific questions on the implementation side. The first question is, are there software libraries commonly used for simulations? That's the first question.
Okay. Yes, there are. So there are a lot of there's no commercial software for this thing. Most codes that are like I have my own code for example, because I was developing it as part of my project. But the astrophysicists who are actually using these codes, they generally come from laboratories like in the US, or there's some groups in the UK, and there are definitely packages that they have. So there's one, I think it's Pluto. The name of the code is Pluto. I think it's Pluto. I might be wrong, but on their website there are basically different packages. One for relativity, one for MHD or something like that. So they actually have to write their own libraries for this. But yeah, I think that answers the question.
Yeah, I think so. In general, even from my experience, we usually use like a linear solver library that we usually have, but that's the best like I can think of, like what are the other libraries. But I think so. Jamie covered that well.
Okay.
So the second question is to the same person as variable cell size / variable time step techniques.
Mm-hmm. Yeah, that's what's the question exactly? It's a good topic to talk about.
Yeah, so implementation, like on the implementation side of like fluid, do you have any like variable cell size slash variable time step techniques?
Yes, so let's say cell size first. There's a technique which is used quite extensively called AMR, which is adaptive mesh refinement. And this is where if you have something like a shockwave, you refine your, you make your cell size smaller, say around the shockwave, so you can get more detail. Or perhaps in the flow, there's more stuff going on over here, so you use more cells in that region, whereas over here there's not much going on, so you can use larger cells. So this is kind of a adaptive technique, which is really useful. This can be tricky to implement, but it certainly exists. I don't use it because I haven't implemented it, but I would quite like it in my code, to be honest. But yeah, that's variable cell size for sure. It's worth noting that most people in astrophysics code, they're using structured grids. I've never actually seen anything in astrophysics with unstructured. I'm not sure. I mean, things get a bit more tricky with unstructured, but it's not necessarily because people don't want to use unstructured. I think that they just maybe they haven't thought about it, like, or because we're generally dealing with simple geometries as well, it might they perhaps don't see much benefit of it. So pretty much structured meshes are always seen. I don't think I've ever seen an unstructured one. And then time step, yeah, sure, variable time stepping. You can implement something to do with that. You have to be careful, but yeah, for sure that's a thing. And also, when I talk about the viscosity stuff, because the time scales are different between the large scale fluid motion and the stuff that happens on the small scales, you have to be really careful with your time step there. And in fact, because the dissipation stuff requires a derivative in time, we actually use different time step for this. So for example, if the bulk motion of the fluids that's delta t, for the viscous stuff, it might be delta t over 4 or something. So we have to do quite a lot of things within that for one time step of the global flow. So it's tricky, and it's kind of a yeah, it's where it all becomes an engineering problem. I don't want to say trickery, but it's where you have to engineer solutions to these equations. So yep.
Okay, thank you so much, Jamie, for that. Definitely AMR is a very, very important thing, and I'm surprised to know that unstructured grids is not a very well-known thing in astrophysics, and it might be true that the geometry is not really very complex in these cases, so really you don't have to, because even like me using, like I personally use like unstructured grids everywhere, and when you deal with something in your wake or like in the fluid part of the things and where the geometry is not there, you don't really use I mean, unstructured grids don't really matter there. Okay, great. With that, I think so we have addressed all the questions. Thank you, Jamie, for that talk. It was really interesting, and I already can see very nice feedback. People received it really well. I apologize for the technical issues that we were facing in between, and hopefully we can try to avoid that in future. So on behalf of the whole organizing committee and also the audience, thank you so much, Jamie, again for this amazing lecture. To all the participants and in the audience, thank you so much for coming and taking your time to attend this amazing lecture that Jamie gave today. We hope to see you soon. If you are interested in attending the Quantum Winter Hackathon, just be sure that you check all the websites and all the emails and links that we send. We will be holding some networking session in order for teams to be made and for hackathon to get started. And we will be announcing soon one of the lectures, which I think so will be the last lecture on the optional list or something like that, which will be on quantum computing, like practical implementation of quantum computing. So if you don't have that background, please try to attend that. That might be helpful for you. The exact date and the time will be announced soon. Apart from that, I think so I've covered all the things. So thank you once again to everyone. Thank you, Jamie. Thank you, people from ISCFD. And thank you, everyone in the audience, to take your time and to attend today's lecture. Thank you, everyone. Have a good night. Stay safe.
Thank you. Stay safe. Yeah.